Good afternoon, everyone. Today we're going to be talking about groundwater pollution. Before we get into that, a reminder that homework number 9 is due on Sunday. Now, that includes a problem where I think you're going to want to use Microsoft Excel. So it's combining the ideas of the Streeter-Phelps model, which is the dissolved oxygen sag. If you computerize that, it makes things really easy. You can change around the variables and find out what is the dissolved oxygen going to be. It takes a little bit of time to set up, but it's the same ideas. It's just a continuation of the same kind of calculations you did in the in-class exercise. So if you have trouble with that spreadsheet problem, I'd encourage you to maybe take a second look at the in-class exercise that we did having to do with dissolved oxygen, because it should be very closely related. 1 week from today, your first draft is due for the research project. 1 week. Has anyone started their research already? Okay, maybe a couple of people. All right, well, this is your 1 week warning that, remember, this is a 2-part research project. Part 1 is a summary of the topic. Part 2 is a synthesis about the ongoing research. Part 1's easier than Part 2, because you don't have to really put any of your independent ideas into it. So you should take the opportunity to get started on that before the night that it's due. It's due by 5 o'clock on Thursday. So you're going to upload that to iLearn. You won't need to print anything for me. You'll upload that to iLearn, and then you'll make an appointment to go to the Writing Center. Next week I'll show you a short video on how the Writing Center works. Any questions on the announcements?
So we don't need to go during this next coming week before this?
No, you don't need to go to the Writing Center before you give me the draft. You should submit the draft on Thursday, and then after you have your draft ready, take the draft to the Writing Center. They can't give you the help until they have something in front of them, some of your writing. Once you give them a draft, they can give you, you can have the appointment with them, but this first submission you'll give to me before you go to the Writing Center. And they'll send me an email telling me that you had the appointment. So if you look at the way the project is being graded, there's some points set aside just for going to that appointment. So if you don't go to the appointment, then it's really going to have an impact on your grade. Other questions related to the announcements? All right, so we're talking about pollution today. Here's a list of the different ways that groundwater can become contaminated. Before we get into the details of this, like how it gets contaminated, why do we care if groundwater is contaminated? Okay, yeah. A lot of drinking water comes from wells. Not so much here as in the rest of the world. You know, here, about 90% of the volume of drinking water is desalination. But still, there is some of the water that goes into wells. Some of the water that comes out of the tap is from wells, and then a lot of the bottled water is also from wells. You know, Masafi, for example, that's bottled groundwater. So if we're drinking it, we want it to be clean, right? These are different ways that the water isn't clean. I've got pictures to illustrate. Let's take a look at those photos and talk about some of the specifics. Broken sewer lines. We have pipes that convey wastewater from residential areas and commercial areas towards a centralized treatment plant. The pipes are buried under the ground. Often they're made out of concrete. That's a typical material. Sometimes this looks like it was a clay pipe, which was sort of an older material to use like a vitrified clay. Even in the past, they would use wooden pipes to transmit wastewater. But if the pipe is cracked, what do you think is going to happen to the wastewater that's flowing through the pipe? It's going to seep into the soil. You know, what we don't see is on the outside of the pipe, and this pipe is surrounded by soil. And so whatever is in that wastewater is going to seep into the soil, and so it's going to be bacteria. If this wastewater includes organic pollutants from maybe an industrial treatment area, like if you have a factory and wastewater coming from a factory, whatever's in that wastewater can get into the groundwater. Another source of groundwater pollution is septic tank discharge. I probably should start by telling you about what is a septic tank. In places where there's not a very high population density, so in rural areas, you know, if my parents live on a farm, for example, they're not going to have a pipe that takes their wastewater 20 miles to the nearest town. I mean, that would be very, very expensive to have a very long pipe for such a low concentration of people. Urban areas usually have sewer lines. Rural areas would have a septic tank. And the way that it works is connected to the house. The waste comes from someone's house into a holding tank. And when the wastewater is in this holding tank, it just breaks down on its own. There's no oxygen being added to this tank, and so it's called an anaerobic breakdown, but there are some bacteria that don't need oxygen, actually. You know, we've been talking so much lately about the bacteria that do need oxygen. I haven't yet told you that there are some bacteria that instead of using oxygen, use other things as their electron acceptors. And so there's bacteria in here that can break down the solids, and so it's in the tank on average. The average holding time inside of the tank is maybe 1 to 3 days, is how long the average molecule of water will spend in here. The solids settle to the bottom. If there's grease or oil, that floats to the top. And then here's a special baffle that draws water only from the middle layer. The clear water will go to what's called a leach field. And a leach field is going to be a network of pipes that's buried underground. Oh, all of these are dried out, I'm afraid. Well, let's see this one. All right. So there would be a series, a main line and then lateral lines, and the water goes out of these lateral lines, and here is the soil. So we're intentionally putting partly treated wastewater into the soil, and what we hope is that the bacteria that are in the soil will naturally break down whatever's left after the water comes out of here. So usually it works fine. In a farm where they're using a septic tank, they're very careful not to put their drinking water well too close to the septic tank. Why do you suppose they're so finicky about that? Yeah, if you want to have, you know, if you're, here is your wastewater and you're pumping out the drinking water, if it's too close, then you're going to get the wastewater into the well. Yep, coliform bacteria. Coliform causes a lot of trouble. In fact, in the United States right now, there's a famous restaurant. It's called Chipotle. And they had to close that restaurant in 2 states, in Washington and Oregon, because people are getting sick from the food. And I think what they found is that coliform may be playing a role in that. So, septic tank discharge. There's 2 ways that septic tanks can cause groundwater pollution. One is the intentional pollution. You know, we expect that a little bit of wastewater is going to be getting into the soil, but hopefully it's only the wastewater components that can be naturally broken down. Or think about, what if this tank gets cracked? Then it's the same problem as this. If the tank gets cracked, then the septage could go into the groundwater. Occasionally, septic tanks have to be pumped out, like the solids that accumulate in the bottom. Maybe every few years, they'll send a truck to vacuum that out. I think there are some places in the Emirates, actually, that have septic tanks as well. It's not only in rural areas. From what I understand, I think there are parts of Ajman that use tanks similar to this for holding wastewater, rather than having a pipe network. All right, so a completely different way. You know, this is just all the list that we're going through today kind of highlights how dangerous it is, humans versus the environment. You know, we do a lot of things that threaten the environment. There's so many different ways that things can go wrong. This is just a list of the many different ways that human activity can, if there's an accident or a problem, pollute the environment. What we see in this picture is a buried gasoline tank. If you've noticed before, when you go to the gas station, they don't have the fuel right next to the pump. Think about how dangerous that would be. If they just had a big tank of gasoline and there's all the cars, everyone's fighting for who gets to go next. They bury the fuel underground and then they have to pump it up from an underground storage tank. It's for safety. It's also for convenience. You know, it gives them more space for parking and so on. However, if you've got a metal tank underground, it's possible that tank can corrode. Sometimes maybe there could be acidic water that causes quicker than expected corrosion, or maybe a company isn't inspecting the tanks as often as they should. And so tanks can actually leak. And here's a photo of an underground storage tank. As they're removing it, you can see that it has holes. And so whatever was stored in that tank, maybe it's gasoline, maybe it's dry cleaning fluid, whatever it is that was in that tank is now in the soil. And since it's in the soil, if they're using groundwater for drinking, then there's a threat. Here's a picture in Canada. Canada is one of the newest oil fields in the world. What they've started doing is, rather than pumping the oil out from underground, in Canada what they're doing is they're actually shoveling huge piles of sand, and then they heat up the sand with very superheated steam, and what it does is the tar that is stuck in that sand kind of melts, and they can, through a really lengthy and expensive and energy-intensive process, they can extract oil from tar sands in Canada. So this is a pipeline that has ruptured in Canada, and you can see it's spraying oil all over the trees. And that's bad for the trees. They're not going to do great after they're sprayed with oil. But it's also bad for the soil underneath that rupture. And so that's another illustration of when you move things around, there can be an accident. Even something as, usually pipelines are very safe. Much safer than moving things by truck, for example. Oop, there's a truck, all right? Just think about how dangerous it is to drive on the freeway here, right? People are flashing their brights at you. That means, I wish you were dead, get out of my way. That's sort of how I feel anytime somebody's flashing their brights at me, is that's really how anxious they are for me to be out of the way. So I usually move over without any argument. But this truck tipped over, and whatever is in that tanker is going to spill into the soil if it ruptures. It so happens that this is a propane tank. And so propane isn't a chemical that would get down into the soil. If this tank breaks open, the propane is going to evaporate because it has a high vapor pressure. But there are plenty of hazardous materials that are being moved around that aren't going to just naturally evaporate. They're going to percolate down into the soil and contaminate the groundwater. Another place pollution can come from is if there is a pond or a lake or even ocean water that's contaminated. Then let me draw a little cross-section of a lake to illustrate the point. Here we have a pond, and so if this is polluted, there's always going to be water coming out of a pond, and it's replenished by the rain. So there's no river going out of this pond. It's just that the water level is regulated by the rain. And so if there is, litter, this photo, maybe you can't see because it's too small, but it's a village in China, and there's all sorts of garbage. I think they dump the garbage in the pond rather than in a landfill. And so the water itself is polluted, the surface water, and the surface water interacts with the groundwater. There used to be a landfill in Sharjah, very close to University City. And maybe some of you who've lived in the area a long time remember that. When I was here the first time around, starting in 2005, there was an enormous landfill, and they were excavating it and moving it. And there's still a little bit of groundwater, there's a little bit of surface water where that landfill used to be. And I would expect that probably that surface water is not the cleanest water in the UAE. Here's a picture from my home state of West Virginia. Where I live, back in the United States, they do a lot of coal mining. And through the process of mining coal, they sometimes have leftover liquids that have to be kept in a pond. They're trying to evaporate it, and so it's a temporary storage pond. It's called a retention pond, and they're supposed to put like a plastic liner underneath that pond while the mining waste is being stored. But plastic rips, right? And plastic can be punctured. Plastic is a little bit permeable, but most of the time a retention pond that's lined has a leak. It's because the liner has been torn or punctured. And so these retention ponds can leak, or once in a while, this is a dam, an artificial dam holding this retention pond. Sometimes the dam will fail, and then that whatever was in there comes washing down the hillside and will infiltrate down into the soil. So that's another illustration of how groundwater can be damaged. Here's a picture of a landfill. Actually, this is a dump. Anybody know the difference between a dump and a landfill? A dump is kind of an informal term. And back in the olden days, when people didn't know much about protecting the environment or didn't care much, what they would do is they would just drive a few miles outside of town. The city would dig a hole, and they'd throw all the garbage into the hole. And it was just as simple as that. The dump was a hole that you threw garbage into. So this is a dump. A landfill is a more specific engineered location for storing waste. This is a picture taken in California where they have they've excavated an area, and then they put compacted clay underneath what has been excavated, and then they put a plastic liner on top of it. And this isn't plastic like the bags that they give you at Carrefour. It's very thick, heavy, high-density polyethylene. And so here's a cutaway that shows what that engineered landfill looks like. First of all, at the very bottom would be 5 feet, which is about 1.5 meters of compacted clay underneath. Anybody know why they use clay as the base for an engineered landfill? That's right. Yeah, so clay is not very permeable. It has a very low hydraulic conductivity. So it's kind of like a backup layer. They want to have so many different levels of protection. They want to have a lot of redundancy in an engineered landfill because when it rains on the garbage, you don't want the water that's inside the landfill to get down into your drinking water. It's better if we just keep the garbage and all of the things that get thrown into the trash. You think about people are putting batteries into the trash, leftover cans of pesticide. Those things really shouldn't be going into the landfill, but inevitably they do. So there's a lot of materials in the waste stream that could pollute our water, and so they go to a lot of effort to try and isolate it. So you can see at the bottom is the layer of clay, and then 60 mils of HDPE, that's high-density polyethylene. So a 60 mil is it's the thickest sheet of plastic you've ever seen. On top of that, they have something called a geonet and a geotextile. The geonet is kind of like a plastic web, and on top of that, the geotextile is sort of like a fabric. It's a very thick fabric, and the purpose of the geotextile and the geonet is to protect the liner, to try and prevent it from getting punctured or ripped. On top of that, there's a layer of high permeability, either sand or it could be gravel. But the purpose of this layer is to make it easy for water to flow to a pipe. Because what they'll do is they'll put a piping network at the bottom here to try and collect whatever water is in there, collect it so that it can be treated. Because you don't want it just to naturally get into, even the compacted clay liner over time is going to transmit water. Not very quickly, but over time it will. So what we want to do is isolate the water so that we can collect it from the leachate pipes, and above that is another layer of geotextile, some sand or soil, and then you can finally on top of that start to have the garbage. So that's the difference between a dump and an engineered landfill. Yeah? An artificial island out of trash? Yeah. In the United States, I one time went skiing on top of trash. Yeah. In Kansas, Kansas is one of the most flat states in the U.S., so it's hard to go snow skiing someplace where it's really flat. We didn't have an indoor ski area like you do here. So their solution was, well, we have a big mountain of trash. Let's cover it up. And so there can be islands out of trash. There can be ski resorts out of trash. Even so, I wouldn't want to live somewhere that had been a landfill or still was. Something about it seems unstable, you know? All right. Other questions about groundwater contamination so far? Yeah. From where people live? They are sometimes very close. And as you might expect, people aren't really happy about living close to a landfill. One time when I was in graduate school, I went and visited a landfill that was under construction. And it was probably within 1 mile of where, about a kilometer from where people lived. And the number one complaint they got from people wasn't the smell. It was that when it was windy, plastic bags would fly, and so there would be plastic bags. So they had to put up a tall fence all around the landfill just to collect the plastic bags. As they're loading it with garbage, it can sometimes take 20 years to fill a landfill. The rules in the United States are that when the garbage is put in, every night you have to cover the garbage with soil. And so they'll make different lifts, as they call them, different layers. When they fill this with garbage, it wouldn't just be solid trash. They fill it with some, maybe a meter of garbage, then they put a layer of soil on top of that. Then the next day, they'll put new garbage on it, a layer of soil. So they're really trying hard to avoid the odor and any waste from escaping. But sometimes they can be extremely close to where people live. What's that? Treating the garbage? Well, I think they sort it. You know, in a lot of places they're trying to take out anything that can be recycled. You know, find the plastic, find the metal. When they put the top layer on it, what they'll sometimes do is they'll have a pipe where they can collect the gas. And so they can generate electricity from the methane that's formed. You know, there's a lot of food waste that goes into the landfill. And when that food waste rots, in the absence of oxygen, it forms methane. So they sometimes do waste to energy and are able to recover a little bit of electricity just from the gases that come from landfills. So let's say that through one of these things, we have now contaminated groundwater. Here's a cross-section that shows the subsurface. And there are a couple of things that's important for you to know. So you can see, obviously, ground level is where the people are living, and beneath that is the soil. Here is unsaturated soil. That means that the voids have some water in them, but there's also air. Air and water in the unsaturated zone. Water table means that below this thick black line, below here, all of the voids are full of water. So the saturated zone means that there may be dissolved gases in the water, but there's no air in the voids. Here you can see at the very bottom is bedrock. And the bedrock is thought of as a layer with very low hydraulic conductivity. The water is flowing sideways. If the bedrock was fractured, then water would be going through the bedrock, but this is one continuous segment of bedrock. And you can have a similar effect if it's a thick layer of clay, where clay would not transmit water downward, and instead water would be flowing sideways. So this diagram is showing that here's a factory, and oftentimes when we have contaminated groundwater, a lot of the times in the past, the way the factories disposed of toxic waste, they would just dig a ditch and pour it into the soil intentionally. And that was common practice through the years up until the 1950s and the early 1960s. So this is a water-soluble contaminant. I've put that in bold because not all contaminants can be dissolved in water, and they'll do different things. But this contaminant, whatever it is able to dissolve and mix with the water as it's flowing sideways. And so it'll contaminate in the unsaturated zone. In the unsaturated zone, whatever this pollutant is sticking to the water that is stuck in the soil. There is some soil moisture, and it's mixed in. There's a little bit of residue, but the majority of the plume is going to get into the contamination plume. The contamination plume is going to move in the same direction as the water that surrounds it. And it's going to diffuse outward, and the plume will getting bigger and bigger. And this is just a cross section. The plume is also getting wider. Let me draw a top view of what this is going to look like. Okay. So now in the top view, we have, here is our factory. Here's the smokestack. We're looking down from above. This is where they used to put all their waste. And the groundwater is flowing this way, underneath the soil. It's flowing to the right as we look down from above. The plume is going to get wider and wider because of diffusion. As it flows, it's going to be moving outward, and you can see it's also going to be getting deeper into the soil. So that's a water-soluble contaminant. Let's take a look at contaminants that aren't dissolved in the water. They're called L-naples and D-naples. That's how you kind of pronounce the abbreviation. L-napple stands for light non-aqueous phase liquids. Non-aqueous phase means it doesn't dissolve in water. Can you think of a chemical that doesn't dissolve in water? Motor oil, right. So if motor oil gets into the soil, it's not going to do this. The motor oil isn't going to dissolve in the water. The motor oil is going to float on top of the water. And that's what's happening here. Another example of a light, non-aqueous phase liquid is gasoline. Light means anything that has the density less than water. So if you're keeping notes on the side of your lecture, what you should write is light means density is less than water. Dense means density is greater than water. Yeah? Turbulent? The water's never moving fast enough underground for it to be turbulent flow. Usually the hydraulic conductivity of soils is so low, and the soil grains keeps the water from moving too quickly. But it would definitely, if the contamination is flowing in a river, then it's going to mix a lot differently. So you're thinking in terms of high velocities from turbulent flow. Okay, so here's the L-napple. Let's take a look at the D-napple, the dense non-aqueous phase liquid. So an example of a liquid that's very dense, mercury. Mercury has a density of 13.6 times the density of water. A liter of mercury would weigh 13.6 kilograms, compared to a liter of water only weighs 1 kilogram. So if we poured mercury onto the soil, the mercury is going to start going through the soil. It'll find the water, and it'll continue to go downward. And then it's going to stop when it finally gets to an impermeable layer, whether it's clay or rocks. Now, L-naples and D-naples, sometimes they'll dissolve a little bit into water. So in the case of gasoline, most of the gasoline is going to stay together, but it's slightly soluble, so some of it is going to dissolve into the water as well. So how would you treat this? What would be your, if someone told you we have a gasoline spill underground, you're an engineer, fix it. What's that? Extract it? Okay, yeah, definitely. We want to get it out of there before it spreads out more. It's always easiest to prevent the spill in the first place, right? Prevention, they say, there's an old saying that an ounce of prevention is worth a pound of cure. meaning that a little bit of prevention is just as effective as lots of treatment. It's better just to avoid it in the first place. Okay, so, but the spill is there. Getting it as soon as possible is going to prevent it from spreading out even to a bigger area. And the bigger the area that you have to treat, the more expensive it is to make the treatment. We're going to talk about remediation, but before we do, let's go through some terminology about the subsurface. Some additional things you need to know. Recharge is where groundwater comes from. And normally what it is it's rain. Rain that has fallen at the surface and that has infiltrated into the soil. What this is showing is that the rain is in the mountains. And this elevated surface area here means that if the rain is in the mountains and then this particular aquifer has a confining layer, this hashed in pattern here means consider it as clay or rock, something that isn't transmitting water very easily. So here, the way that the clay is shaped means that some of this water is kind of pressurized. This section of the aquifer has a higher pressure because of where the recharge is. There's also an unconfined section of the aquifer, but a confined aquifer, this word here means that there's a confining layer on top and on bottom, so that the water is trapped, and it'll also be under pressure. That's why maybe you've seen an artesian well before, where the water is just bubbling out of the ground. And the reason why you'd sometimes see water bubbling out of the ground like a spring is because somewhere, if you're ever at a spring, look around. Because chances are good that there's mountains somewhere nearby, and the reason why you see the spring where you do is because it's raining on the mountains and it's kind of pressurizing, almost like a water tank. This is almost like a water tank. And so here, the water elevation from recharge is higher than where the water is actually coming out. What we're going to be doing today for the in-class exercise is some calculations that have to do with pumping water out of an aquifer. We're going to use Darcys Law, or kind of an adaptation of Darcys Law. And what I hope you remember from your soil mechanics days is that Darcys Law talks about a certain element of soil. And we did a little bit of this when we were talking about sand filters back in the water treatment section of the course. If you have a tank connected to either side of a segment of soil and there's more pressure upstream than downstream, water is going to be pushed through the soil. And it's going to be pushed through, we're going to consider the cross-sectional area of soil, how far apart these two tanks are, the length, and delta H is the difference in head between them. So that Darcys Law tells us what the flow rate will be as a function of some special parameter K. And that K is the hydraulic conductivity, and it tells you how easily water passes through soil. Clay has a very low hydraulic conductivity because it has very small pores. And also, the clay is attracted to the water. And so when the water passes through the clay is trying to hold on to it. Sand, on the other hand, has a much higher hydraulic conductivity because the voids are so much larger in sand. And so the water can seep through it more quickly because the pipes, you can think of the voids as a series of interconnected pipes, the voids are so much larger. So this is Darcys Law that tells us how easily water moves through soil. For a certain difference in head, for a certain delta H, how much flow you can get through the water. This is what happens when you pump water from underground. It causes a cone of depression. I always think that's kind of a funny phrase. Like we're talking about wells and pumps, and this is engineering stuff, but it's also, depression is used to describe like how we feel, So sometimes I think of, oh, I'm entering the cone of depression, but anyways, that joke aside, water is coming out of the aquifer and it's flowing towards wherever the well casing is. So underground we dig a hole and we put screening, as it's called. We put like a wire mesh. It's not just a solid pipe. If it was a solid pipe all the way to bedrock, then water couldn't get into the pipe. So it has to be a slotted pipe with holes in it. So the water goes towards it, and the closer you get to the well, it's actually drawing the water down. And that's why the water moves towards the well. This is in equilibrium here for a certain flow rate, it's going to cause where the water table used to be, it's called drawdown. The distance between where the water level used to be and now where it is during the cone of depression. So here's the remediation I was talking about earlier. How do we fix it? This is showing a lot of different kinds of remediation. We'll take just a couple minutes to talk about what we see. This happens to be the situation of a landfill that has breached. So whatever is in that landfill, maybe it's battery acid, or it could be chemicals that people put into the garbage that they should have taken for hazardous waste collection, but they didn't. So there's bad stuff in the landfill, and it got into the water. Here you can see a dissolved VOC plume. VOC stands for volatile organic compound. So it's something we have to get out of there. So one of the things that they're doing to remediate is soil vapor extraction. SVE means that they have a big fan at the surface and they're blowing air into the soil, into the vadose zone. Vadose zone is just another word for the unsaturated zone. It's the soil that has some air in the pores above the water table. If you blow a bunch of air into the soil, it can make it evaporate. And so these volatile organic compounds like gasoline, if you pour gasoline on the ground, eventually it'll evaporate. So the whole point of soil vapor extraction is to try and get a little bit of air underground to try and help the contaminant to evaporate. So that's one strategy. Another strategy that is illustrated here is they're injecting water in one location and they're extracting it in another, and the water that they extract is contaminated water. And so they put the contaminated water through a filter. And what kind of a filter have you heard about that will take out organic materials? We've talked about it in this class before. I'm wondering if anybody remembers. It's a filter that is especially attracted to organic materials. Remember, organic compounds, like an organic chemical, is something that has a carbon-hydrogen bond. Activated carbon. Excellent. Good. I'm glad you remembered that. So what they're saying is you take water, you pump some water underground, and you're kind of like flushing it out. Like we have all of this spilled gasoline underground. One of the ways we can remove it is you inject clean water, the clean water flushes through the contaminated area, and then you pump that contaminated water out and put it through the activated carbon. When I was in graduate school, I visited a site one time where the government had been making explosives. It was during World War II in the United States, there were lots of places where they'd make explosives, and so at this big explosives factory, they put the leftover explosives on the soil, and it got into the groundwater there. And there's something called RDX. It stands for Royal Demolition Explosives. It's a British explosive. And this particular was a small town. It was a nice little town that you'd never expect, but they had to filter explosives out of the drinking water before it went to people's house. I don't think it probably would have exploded in their house. It was low concentrations, but probably not good to be drinking RDX. So those are two different kinds of remediation. So the calculations that you're going to do today are focusing on how pumps behave in taking out contaminated water. We've already talked about hydraulic conductivity. B is a variable we're going to assign to aquifer thickness. I'll show you a picture in just a minute. The other thing that's important is transmissivity. If you multiply the thickness of an aquifer and its hydraulic conductivity, that's what transmissivity is. So let me jump through the other ones so I can show you this picture. This is a confined aquifer with an occluding layer on top and another layer on bottom. And these two layers don't allow water to pass through very easily. But this layer does, the one in the middle, the aquifer layer. So here you can see the piezometric surface, and there's drawdown here because pumping is happening from the well. what I'd like you to do is get a feel for how these calculations work. I've given you an in-class exercise with the equation for both the well equation and the transmissivity equation. The variables are defined in the problem statement. So what we want to do is find out what's the flow rate in the well. So part A is solved for Q. Let me give you one hint though, and it's on the drawing, but I want to make it very clear. We talk about location 1 and location 2 in this equation. You know, H is the height of the water, and R is the radius, how far away from the center of the well you are to a certain location. 1 is always the location that's closest to the well, and 2 is always the location that's further away from the well. So here in the problem statement, in part A, talk about two different locations. I talk about one that is 85 meters from the well and one that is 40 meters from the well. The hint is 1 should always be the one that's closest to the well. All right, go ahead and get started. Good morning. Yeah. R means the distance from the center of the well to the point in question. In part B, you're going to have to use the well diameter.
Surface, you mean the head law?
No, we're talking about, in piezometric surface, it means the distance from the bottom of the well to that line. That's the piezometric surface. You see, it's labeled here, piezometric surface. So it's this one. You woke up? Yeah. For part B? Yeah. Yeah, you use the same equation in part B. Yeah, in part B, you're going to be solving for H1. So do part A, and I think you'll see how you can rearrange the same equation in part B. Okay, here's the in-class exercise and the solution. Any questions about this one? We didn't have to use 40 meters for the R2. We could have used 80, but then you'd have to use whatever the height of the water is at location 2 for that specific location. This is called the theme equation. And it's used a lot in hydrology, especially subsurface hydrology, trying to predict how much water you can get from a well. So if they're doing a pump and treat, trying to get the polluted water out of there, they're going to have the water drawing down in one location, and they'll probably inject the clean water somewhere else. So instead of draw down, what they would have where they're injecting the water is the water is mounding up. So let's say that what we're trying to do, here's our pumping. The water draws down there, and so if we re-inject the water here, then it's actually going to look like that, if this is an injection well. It's the opposite of drawdown. Okay, so on your way out, please submit your in-class exercise. As a reminder, your next homework assignment is due in class on Sunday. Hope you have a good weekend. I'll see you then. What? Will I post this on Island? No, I hadn't planned on it. This one? Okay, yeah, I'll post it online. Yeah. Was there another question?
What is balance process?
Oh, I don't know. Let's pull up...